Recording. Hello, everyone. We're the team. We're Dance, and we participated in the Imperial College Data Science Society, the Hackathlon 2021. And we're implementing a machine learning model to predict crop yields at Illinois 2 months prior to the harvest time. So first, we looked at this EVI data, which is the measure of the greenness of crops in different areas of Illinois, also coordinated by the latitude and longitude. And from the plot, we can see the distribution of EVI at Illinois is exceptionally low at at water bodies such as the River Mississippi and the Michigan Lake. And also we can see the distribution of EVI over a year is peaking in June and July time, so around summer. And the yields that we are investigating increases annually over time from 2001 till 2019, except from a drop in 2012, which is due to a drought caused by some under-recovered wells in 2011. Then we move down to looking at the temperature changes in the time period that we're observing, which is from 2001 to 2019. We can see that there hasn't been very much extreme weather, such as extreme temperatures at Illinois during this time, but there has been some lower than usual winters recorded in 2012 and 2013. And looking at the plot on the top right, we have found some data sparsity in some of the counties at Illinois, and this may result in some high variance predictions in our results.
Hi. So this is a display of the data frame that we used on how we combined all the given data sets together into this final data frame, and we tested our machine learning models on this. Next, please. So here we have, these are the first three models that we tested out before moving on to our final model. So model 1 is a neural network model, model 2 is a decision tree model, and model 3 is a random forest model. So on the top left corner, you can see that the validation loss from the test set decreases over time and then stabilizes around 300 epoch, and so does the loss set. The fact that so does the loss set on the training data set. The fact that these two lines intersect, it means that we are not doing any overfitting in our models. In our model 1, you can see that all the errors are somewhat normal distributed, with the variance around 0.9, which is close to 1 for normal distribution. In this plot, below the error plot, the red line shows you the y-test against the y-test, and then the blue dots are y-test versus the predictions. So you can see that the predictions are close to the true values. Now, out of all these three models, the root mean squared error for random forest and the means absolute error for the random forest is the lowest. Next, please.
Right, okay, so the final model chosen was an ensemble model between a random forest and a neural network. So even though the random forest gave more accurate predictions, the reason why we used an ensemble was because random forests alone give bad predictions outside of data that they've seen. So the neural network is used for future proofing. Say, for example, if there are future extreme weather events. In that case, our model would actually be helpful. Metrics show that this combined model still has a low bias and low variance, and so it's what we finally used. Different ensembling techniques were used, and since all of them were fairly consistent with each other, we used the simplest one. Next slide, please. We did feature importance on the random forest part of the final model. And it turns out that the most important features for predicting yield by far were latitude and longitude, so the geographical location of our crops, as well as the temperatures at very specific parts of the year. The plot on the right is fantastic. It's a waterfall plot, and it's a great visualization technique that shows how the yield changes, how the predicted yield changes of our model as we give it more data. So we see at first there is a certain yield, and then once it sees, there's a longitude, that's a certain point, then the yield prediction increases, and then it goes up and then goes down. And then finally, after seeing everything, it thinks, okay, the final yield is 30 less than just the average of all the yields that we usually would get. Next slide, please. It's also important to know how confident our model was in its predictions. And we did this by finding variation between the trees used in the random forest, and we found that our model was quite confident in what it was doing. The table on the left actually shows the most deviated predictions, and having a deviation of only 1.6 in yields that vary from 4 to 246 is absolutely fantastic. Next slide, please. We also did partial plots for all the data our model used. So just to recap, we used temperature, EVI, and geospatial data for our model to predict yields. So by doing partial plots of temperature, what we could do is we could actually predict how the yield changes if, say, the temperature in April in a specific day goes up or down. And the plots show that under temp 105, that shows that around the 100 days into the year, if the temperature is too extreme, then the yield decreases quite a bit. And it's quite good between 290 and 295 Kelvin. And it turns out that according to expert advice, when it comes to planting corn and soya, that the best temperature to plant corn and soya would be around that little hump that we get in one of our graphs. And it's fine for us to just think of all the crops as being corn or soya, since 95% of crops in Illinois are corn and soya. Finally, 100 days after the corn and soya are plotted, we see that if the temperatures are too extreme, so this is around June, if the temperatures are too extreme, then the yield decreases quite a bit. And we could interpret this by saying, okay, if there's a drought, if it's very dry and hot, then of course the yields are going to be different. But it's fantastic that without actually telling our model this, our model was able to infer this from just temperature and yield data. Next slide, please. So the location at which you plant crops in Illinois was a huge predictor for yield, the biggest one. The overlay on the right summarizes it very nicely. Here, the lighter the color, the more yield we would generally predict in this part of Illinois. We see how in the northwest region of Illinois, that is the area at which we'd expect the most yield generally. And although this hasn't been statistically verified yet, I believe that latitude and longitude encodes soil moisture data for Illinois. The reason being that the south part of Illinois has the Amazon and the Utah River flowing next to them, which would give soil that's too moist for corn and soya to grow successfully. Next slide, please. Finally, the EVI index changes were shown to change yield predictions quite suddenly. And a way to summarize this would be the greener the crop, the bigger the drop, where the drop is like how much yield we get. The EVI changes were only found significant at very specific days. And it turns out that at the days at which they were significant, this was when corn growth, the corn was reaching its maturation stages of growth. It's interesting that none of our models actually used EVI data for predictions significantly, even though our partial plots found a pretty strong correlation with them. Great, thank you.
In conclusion, we can say that our model does have business importance because it's able to predict the crop yield for the end of the year 2 months in advance of harvest time. Our final model combined neural network and random forest. We came up with data analysis that showed that And our machine learning model suggested that there was strong relationship between air temperature during seeding and annual yield. Early growth of corn and soybean favors higher temperature and soil moisture. There was a strong relationship of EVI in late May, and early June. This is the seeding period with annual yield. The progression of the crop is really determined by the first 100 days after seeding in determining the yield. Thank you for listening.